Okay, in this video, I want to go over the section 12.3, which is the last section of chapter 12 in our class, and it's talking about the regression equation. In 12.1 and 12.2, we talked about the correlation, and we learned how we can verify that the two variables have a linear correlation. Now, after verifying that there is a linear correlation between the two variables and the linear coefficient, and that correlation is significant, the next step is finding the equation of that line. When we say there is a linear correlation between the two variables, that means if we plot the points on a coordinate plane, we can find a line, which is called the regression line, between the points, and it's also called the best line of fit, which means that it's a line that fits or is close to the most of the points. And finding the equation of regression line helps us to predict the value of y for other given values of x, even if it's not in the data set. If we have any values of x, by using the equation, we can predict the y. To find the equation of the regression line, or to find the regression line actually, we need a line between the points that has the minimum residual. What is a residual? Residuals are the distance between the observed point, the actual points, like this, and the point that the regression line represent on that specific x value. For example, if you in this coordinate plane, if this is one x value, there is a y value for that x value, which represented by the point, by the observed point, and there is another y value, which is called the predicted y value. And the difference between these two y values is called d. So the d is this difference between the observed y value from the point and the predicted y value. And these residuals, which we show them by d sub I, d1, d2, d3, based on which point on the scatter plot we are looking at, can be positive and can be negative. They can be negative if the point is under the line, if the observed point is under the line and it has a smaller y value, and it can be positive if the point is above the line, which means we have a greater observed value. We have a greater y value than the predicted one. And any line between the points that has the minimum, that the sum of the s square of those residuals is minimum, that means that is the regression line, and that's the line of best fit. Okay, now we call it a line. Every line has an equation. How we can write the equation of that line, as we learn in all of the elementary and middle schools, high schools, college, their equation of the line is always y equal mx plus b, which m is the slope and the y is the b is the y-intercept. But in this case, since the regression line is a line that fit with the points, but it's not actually going over all of the points. And you see, there is always a residuals between the points and the line. So the line may pass over some points, but may not pass on the others. So whatever the line represents to us, whatever y value that the line represents to us, it's called the predicted y value, and we show it by y hat. Y hat is the predicted y value, and that's the exact y value that we get it from the regression line. It's not the exact y value from that point. The only time this can be the exact y value if the line goes exactly over the point. So now the question is, if we have this equation for a regression line, how we can write this equation, how we can find the slope and the y-intercept to write the equation. To find the slope, we need to know the standard deviation of all of the y values and the standard deviation of all of the x values, divide by each other, and then multiply by the correlation coefficient. We learned in 12.1 and 12.2 how we can find R. There are online calculators, TI calculators, or you can use formula to find R by hand. After finding the correlation coefficient or R, we also need the standard deviation of all of the y values, the standard deviation of all of the x values, and then using this formula to find the slope. Or we can use this formula to find the slope by having the x values and the y values only, not depending on R. And after finding the slope, now to find the y-intercept, we only need to plug in the numbers into the equation. To the same equation, but instead of x and y, we use x bar and y bar, which is the mean of the x value and the mean of the y values. So what do we need to write the equation of a regression line by hand? We need, because whenever they ask you to find the equation of regression line, that means you have two sets of data, one for x values, one for y values. And you need to find the mean of all x values and the standard deviation of all x values. You need to find the mean of all y values and the mean of all of the y values. And by having these two from each sets of data, you can find the slope and you can find the y-intercept. And then using the formulas to find the slope and the y-intercept, and then you're done. You can write your equation. If you want to use formulas and work on the problem manual. For example, we have a given data set. And it asks us to find the equation of the regression. To find the equation of regression line, as I said, we need to know what's x bar, what is the standard deviation of x, what is y bar or the mean of y values, and what's the standard deviation of y values. So you can just put these numbers on the x values and then find the mean. The mean is 10.83. And the standard deviation of all x values is 2.317. To find, just then you put all of the values for y, and you get that the mean of the y values is 7, and the standard deviation of y values is 2.280. Then you also need to know the R. And if you remember the formula for R, that was a huge formula, which we needed all of the x values, y values, square them, add them, then square, multiply them, add them. That had a lot of steps to find R. You can work it manually, but I recommend you always use online calculators or TI calculators. And after having all these, you finding the R, then you can find the slope by you having the formula, and then find the B by plugging in this formula. But I want to show you how you can use online calculator to find all this information. Okay, so if you look at the list of online calculators, you will see that number 24 is called regression analysis. And if you click on this calculator, you will get this calculator. And it asks you to type in all of the x values and the y values. And I typed in all of the x values and y values to save time. And you see the x values are 10, 8, 13, 9, 11, and 14. I put it here without any space with just comma between. And I put all of the y values, and then I pressed plot points. When you press plot points, it gives you a scatter plot. It gives you a coordinate plane with all of the points on it, and also the line of best fit, which is the regression line. And it also gives you the equation of the regression line, which means you don't have to calculate it manually. But if you want to calculate it, you can also use R with the other information that I gave it to you, and then put it in the formula and find the slope and y-intercept. If you have any hypothesis test that we explained it on 12.2, you can also use these t-value and these p-value for the purpose of your hypothesis test. Let's look at another example. Okay. So I will show you next example after explaining these slides. What is R square? We know that the R is the correlation coefficient. When the R square is called the coefficient of determination. Coefficient of determination, which is the S square of the correlation coefficient, and it's usually stated by the percent. It tells us the total variation in Y values, which is explained by the X values, which is explained by the X values in the regression line. And you know that R is always a number between -1 to 1. But if you S square R, you always get a number between 0 to 1. What does it mean if R square, or the coefficient of determination, is equal to 0? It means that this model, this regression line, explains none of the variability. What if R square is equal to 1? It means the model, the regression line, is a perfect fit, which means that the model explains all the variabilities. And if we get any number between 0 to 1, we can say how many percentage of the variation explained in Y values explained by the X. For example, if R square is 0.8, it means that the 80% of the variation in the Y is explained by the X. And it depends, in any example, it depends based on what is the X and what is the Y variable in that example. You can explain that for 80% of that, of the variation in the Y value, or whatever it is in that example, is explained by the X value, which you need to know what's the X value in your example. For example, it says, suppose you're using a simple linear regression model to predict the house prices, which is Y, based on the size of house, which is X. So in this example, I have two variables, X and Y. X is the house price, X is the size of the house, and the Y is the house price. And in this table, you will see that the X values, the house sizes in square feet, and you see that the actual price of the Y values, and you also see the predicted Y values, which comes from the regression line. And if you calculate the R square in this example, you will see that the R square is 0.889. And since we usually represent the R square in percent, it means that the 88.9% is the R square. And it means that the regression line in this example shows that the 88.9% of the variability in the Y value explained by the X value. Now the question is, what is a Y value? The house price. What is the X value? Size of house. Which means we need to say that 88.9% of the variability in house prices, based on this table, is explained by the size of houses. And we can also say that the remaining 11.1% of the variability, which is not explained in this regression model, is due to other factors, which is not captured by this model, such as the location of the house, the age of the house, or the market conditions. So remember that that the coefficient of determination, or R square, represent the percentage of variation which in Y value, which explained based on the X value in your model, in your regression equation. Now, let's see how we can work on another example. I have another example for you. Okay, let's look at this example. It says that what is the relationship between the amount of time statistics students study per week and the final exam score? So we have two variables: the amount of time that the students study per week and the final exam score. And we want to see if there is any relationship between these two variables. And the table is given. The student who spent 13 hours per week, he received 100% in the final exam score. One student who spent 5 hours in a week received 54 in the final exam. Another student, again, who studied 13 hours per week, received 89 in the final exam. Now it's asking you find the correlation coefficient, or R. Okay, again, when you open the online calculator, you need to open the calculator number 24. When you open calculator number 24, it asks you to put all of the X and all of the Y values. Okay, all of the X values, 13. X values are the time, Y values are the score. X values are 13, 5, 13, 16, 14, 7, 4, 5. And the Y values are 100, 54, 89, 93, and you see all the numbers here. Now I press plot point. When I press plot point, you will see that the points are on the coordinate plane with the line of best fit. And you can also see the equation of the regression line. You can also see the R, which is 0.82. Okay, so you can type in 0.82 for R. Is R 0.82? Yes, you can see the answer here is 0.82. Now it's asking you to write a null and alternative hypothesis for the correlation. So to write a null and alternative hypothesis, I told you that you can use the rho, because the rho is for the correlation coefficient. So when we check the factors here, the notation, we see there is only R and mu. There is no rho. But mu doesn't make sense because we're not talking about the mean or average. We are talking about the correlation. So we have to choose R. And we always put the not equal sign for the alternative and equal sign for the null. So the null, it says R is equal to 0, which means there is no correlation. And the alternative says that R must be not equal to 0, which means there is a correlation. There is a significant correlation. Now it's asking you to find a p-value. I'll go back to the calculator and see the p-value is 0.00679. And if we are supposed to round it to 4, we get 0.0068. Let's see the answer. 0.0068. Yes. Now it's asking that if the level of significance, or alpha, is 0.05, state the conclusion of the hypothesis test. So we always compare the p-value with alpha to make the conclusion. Right now, p-value is less than alpha because p-value has 2 zeros before a number, but the alpha has 1 zero. So 0.006 is less than 0.05. And whenever the p-value is less than alpha, we reject the null hypothesis. So when we reject the null hypothesis, that means we can support the alternative. And the alternative says that there is a significant correlation because R is not equal to 0. So when you read this conclusion, The first one says there is a statistically significant evidence to conclude that there is a correlation between the time spent studying and the score on the final exam. Thus, the regression line is useful. Yes, that makes sense. Number two, it says there is a statistically insignificant. Nope, doesn't make sense. There is a statistically significant evidence to conclude that the student who spend more time studying will score higher or less than. Nope. And there is a statistically insignificant. Again, no. So the answer is the first one. There is statistically significant evidence to conclude that there is a correlation between the time that students spend studying and the final exams. Now, what is R square? R square is the coefficient of determination. So go back to the calculator, and the R square is 0.0672. And if you round it to 2, it's 0.67. That should be enough, 0.67. And now he's asking you interpret R square. You know that coefficient of determination always represented as a percentage. When you have 0.67, when you round it to 2 decimal digits, that means you can claim that the 67% of the variation in y values explained in this model with x values. And you know that the x values are the time that the student spent, the y values are the score they received on the final exam, which means that 67 of the variation in the final exam score explained based on the time that the student spent on this to studying for the exam. Now let's see which one of these can make sense for us. It says, given any group that spends a fixed amount of time studying per week, no, we don't have a fixed amount of time because each student have different time. So we can skip this one. It says there is a 67% chance that the regression line will be a good predictor for the final exam. 67% for the R square is not a 67% chance. That's not the probability. That's the percentage of variation. So we ignore this one as well. Next one is a 67% of the variation in the final exam score that the student receive is connected to the amount of time they spend studying each week, which means 67% of variation in the y value explained by x value. Yes, that's the answer. And if we check the answer, we see that's exactly correct answer. Now, next part is asking you to write the equation of the regression line. Equation of the regression line, again, we have it on the online calculator. It's 45.5 plus 3.19x. 45, let me show you the answer. 45.5 plus 3.19x. That's the equation of the regression line. Okay. Now, next part, it says use this model to predict the final exam score for a student who spent 8 hours per week studying. So you know that in the prediction model that we have the equation here, x is the amount of time that the student is spending, y hat, which is the predicted y value, it's the predicted final exam scores. That means by replacing x by 8, we can find the predicted final exam that the student receive after 8 hours studying per week. So whenever you have a number for x, you want to find the predicted y value, you just plug in the number into the equation. So we replace the x by 8 into this equation. So what do we get? So we will have y hat, which is equal to 45.5 plus 3.19 times 8. Replace the x by 8. And you know that the order operation tells you multiply these two first and then add it by 45.5. And the final exam for the predicted y value should be 71.02. That means if, based on this model, if a student spend 8 hours per week studying, the predicted final exam score can be 71. So we replace the 71.2 here, and the answer is 71.2. Yes, that's correct. Now it's I tell you, interpret the slope of the regression line. The slope of the regression line means the number that's in front of the x, which is 3.19. What does the 3.19 means? You know that always the slope is a number that's in front of the x. And since that's a number in front of the x, it can be explained like 3.19 per x. X is the amount of time the student is studying. That means 3.19 per hours of studying. That means per hour, per one additional hour that the student is spending, he can have a 3.19 on the scored average. We can, the student can receive that average higher. For one additional hour, they can have an average of 3.19 higher score. That's what it means. That's what the slope means. For every 1 hour, for every 1x, we have 3.19. For every 1 hour studying, we have 3.19 on the final exam score. Okay, so let's see what option do we have here. It says for every additional hour per week students spend studying, they tend to score an average 3.19 higher on the final exam. Does it make sense? Yes. As x goes up, y goes up. Not exactly. The slope has no practical meaning since you cannot predict what any individual student will score on the final. No, because we have a model, so we may be able to predict. Because the p-value was greater than the significance level, but it wasn't because p-value was less than. So that's the only one that makes sense. And if I check the answer, you see, yes, that's correct. It's for every additional hour that students spending studying, they will receive an average of 3.19 higher score on the final exam. Now, if I want to interpret the y-intercept, the y-intercept is the number that doesn't have any x, which is 45.5. That's my y-intercept. And the y-intercept is always a number when the x is 0. When you have y hat, which is 45.5, 3.19x, if you replace the x by 0, what happens? 3.19 times 0 is just a 0. That means you receive y hat 45.5. That means your y-intercept, that's exactly your predicted y value. Or the y-intercept is the predicted final exam score. So what we can say the average final exam score is predicted to be 46. That's rounding to 46. The average final exam is predicted to be 46. It's not the average final exam score. It's just a predicted one for every student. The y-intercept has no practical meaning. No, if a student does not study at all, what does it mean if student does not study at all? That means if the x is 0. Then that student will score 46 on the final exam. Yes, that's correct. Because if you replace the x by 0, we get that the predicted final exam score, that's 45.5. So if the student does not study at all, then the student will score 46. Yeah, that makes sense. The p-value was greater than the significance level? No, it wasn't. The best prediction for a student who doesn't study at all is that the student will score 46? No. So that's only one. And if I check the answer, you see that yes, the best Oh, we didn't read the last one carefully. The best prediction for a student who doesn't study at all. Yes, this doesn't study at all means exact again that when the x is 0. The best prediction, yes, that is a good point. We didn't pay attention because the y hat, that's a prediction y value. If the student doesn't study at all, doesn't mean that receive 46. Our prediction is 46. So the best prediction for a student who does not study at all is that the student will score 46 on the final exam. So that is the good one. So we have to pay attention. I hope that helps.